Yeah, just on this mouse battery is gone, is it?
Oh, sir, it's there, sir.
Yes. Okay, fine. Yeah.
Once you're ready, you can start, sir.
Yeah. So far we have discussed the definition of dimensionless groups for mass, heat and momentum transfer, how the characteristic lengths are defined, the equivalent diameters, the hydraulic radius, how the velocities are defined, the average velocity or the free stream velocity, and how the average fluxes are defined, okay, for mass, momentum and energy. In this class we will start taking a closer look at the correlations for different kinds of transport, starting with momentum transfer. Okay. And this is we start with momentum transfer because the fluid velocity field is obtained by solving the momentum equations. Okay. So solving for the fluid velocity field is a momentum transfer problem. Once you know the velocity field, then you can put that into the equations for mass and heat transfer and then solve for the temperature or the concentration fields. Okay. So the temperature and concentration fields depend upon the velocity field. In general, in the simplest case, the velocity field does not depend upon the temperature and concentration fields, provided the properties, the viscosity, the density and so on are independent of temperature or composition. Okay. So, that is why we start with momentum transfer. Okay. The simplest problem of momentum transfer for an internal flow is a flow in a pipe, okay, length L, diameter D. Okay. We will see a little later that the velocity profile across the pipe is a function of position, okay, but we define the average velocity as flow rate by cross sectional area. Okay, this is the average velocity. Okay, the average velocity is defined as the flow rate divided by the cross sectional area, and the diameter is the diameter of the pipe. Okay, this is the characteristic length scale for the pipe. Okay. The Reynolds number is defined as the density average velocity times the diameter divided by the viscosity. Okay. So, that is the definition of the Reynolds number. Okay. And the friction factor, the scaled momentum transfer rate, okay, the scaled momentum flux, okay, is the friction factor, which is defined as the wall shear stress divided by the kinetic energy density. Okay. I had told you earlier that this definition is what is called the Fanning friction factor. The Darcy friction factor is 4 times this. Okay. And by momentum balance, we know that the wall shear stress is related to the pressure gradient, the pressure difference across the pipe per unit length. Okay. So, we had derived this relation by momentum balance, that minus delta P by L is equal to 4 tau W by the diameter. Okay. By just balancing the stress exerted by the fluid on the walls of the surface of the pipe with the force exerted by the difference in pressure across the two ends. Pressure times the cross sectional area, difference times the cross sectional area is equal to the wall shear stress times the curved surface area, and that gave us this relation. and based upon that this can also be written as delta P by L by 2 rho V average square. Okay. So, this is the Fanning friction factor, and the Darcy friction factor is defined as 4 times that. Okay. Now, the flow in a pipe, okay, there are two distinct regimes for the flow in a pipe. Okay. What is called a laminar flow and a turbulent flow. Okay. So, for the laminar flow in a pipe, okay, the velocity profile is a parabolic profile. Okay. The velocity profile is a parabolic profile. Okay. The streamlines are all nice and smooth and straight, okay, and there are no fluctuations in the fluid velocity. Okay. There are of course fluctuations in the molecular velocity always, but the fluid velocity does not have fluctuations in the direction perpendicular to flow, okay, which means that transport in the direction perpendicular to flow has to happen necessarily due to diffusion, okay, and that is what is called a laminar flow. Okay. This happens when the Reynolds number is less than approximately 2100. Okay. Okay, this number of 2100 is not a hard and fast rule. Okay. If you take care to damp out fluctuations in the inlet of the pipe, right, so that there are no disturbances, then you can maintain the flow at even a higher Reynolds number. But in normal situations where there are disturbances in normal equipment, this transition takes place at a Reynolds number of about 2100. Okay. When the Reynolds number exceeds about 2100, there is a transition to a different kind of velocity profile called a turbulent profile. Okay. The flow becomes what is called turbulent. Okay. When the Reynolds number exceeds approximately 2100. Okay. And in this case the flow is no longer steady. There are local cross stream fluctuations, okay, of different sizes. Okay. At a given location, even though the velocity is in the streamwise direction on average, right, instantaneously there are fluctuations in all three directions. Okay. So, there are large fluctuations in all three directions locally at each point within the flow, okay, even when the pressure applied pressure difference is steady. Okay. Even when there are no fluctuations in the applied pressure difference that is driving the flow spontaneously generates fluctuations within all three directions. These are by what are called correlated motion of parcels of fluid, which are called as eddies. Okay. By correlated parcels of fluid, okay, by parcels of fluid in correlated motion called eddies, okay, which cause velocity fluctuations in all three directions. Okay. The velocity profile is flatter at the center, okay, than a laminar flow, but it has a steeper gradient at the wall in comparison to a laminar flow. Okay. What that means is that the slope of the velocity profile at the flow for a laminar flow, okay, there is a slope. The slope of the velocity profile for a turbulent flow is higher than the slope of the velocity profile for a laminar flow at the wall. However, near the center it is flatter. Okay. It does not have the curvature of a parabola. It is flatter than and more plug like than a laminar flow. In a laminar flow, the cross stream transport of mass, energy, momentum takes place due to molecular diffusion, okay, because there are no fluid velocity fluctuations in a laminar flow. In contrast, for a turbulent flow, the cross stream fluctuations cause a transport of mass, momentum and energy across the flow. Okay. These are fluid velocity fluctuations, not molecular velocity fluctuations. Okay. So, the length scale of these velocity fluctuations is much larger than the molecular length scale, and it is comparable to the diameter of the pipe or the size of the conduit. Okay. So, these are large scale fluctuations in all three directions at each point in the flow, which transport mass, momentum and energy across the flow. The mechanism of transport is due to the fluid velocity fluctuations. This mechanism is far more efficient than the transport due to diffusion due to molecular velocity fluctuations. And because of that, the transport coefficients in a turbulent flow typically are much larger than those in a laminar flow. Okay. The Nusselt number and the Sherwood number for a turbulent flow at the same flow rate would typically be much larger than those in a laminar flow. Because momentum is also transferred across the flow by the fluid velocity fluctuations, the friction factor also for a turbulent flow is much larger than that for a laminar flow. Okay. So, these are two distinct regimes with two distinct properties, and the transport properties will depend upon which regime one is operating in. Okay. So, in order to find out what is the flow characteristics, first the Reynolds number has to be calculated. The transition depends only upon the Reynolds number, the combination, the dimensionless combination of the velocity, the characteristic length, the density and the viscosity. Okay. It does not depend individually on a dimensional quantity like the velocity. Okay. So, in order to find out whether the flow is laminar or turbulent, the first thing we have to do is to calculate what is the Reynolds number for the flow based upon the average flow velocity, okay, or the flow rate divided by the cross sectional area. Now, if one is in the laminar regime, okay, then the inertial terms, inertia is no longer important. Okay. So, therefore, the wall shear stress has to depend only upon the viscosity. Okay. Inertia is no longer a parameter in the laminar flow regime for a cylindrical pipe, okay, up to a Reynolds number of about 2100 or so. Okay. And therefore, the friction factor has to depend only upon the viscosity. Okay. And from dimensional analysis, it is quite easy to infer what that form will be. Okay. Wall shear stress okay, will depend upon the viscosity, the average velocity and the diameter just from dimensional analysis. The right side of this equation has to have the same dimension as the right side of Newton's law of viscosity, if you recall. Okay. So, it has to be some coefficient. Okay. So, I will write this as a proportionality rather than an equality. If the flow is laminar, density is no longer a parameter that determines the wall shear stress, which means that the wall shear stress has to depend only upon the viscosity, the average velocity and the diameter. Okay. Which implies that the friction factor, which is equal to wall shear stress divided by half rho VAV square, will be proportional to mu by rho V average times d, okay, which is proportional to 1 over Reynolds number. Okay. So, therefore, in the laminar regime, the friction factor is proportional to 1 over Reynolds number. Okay. And we can do a calculation to find out the exact relationship. It turns out that the friction factor, the fanning friction factor is equal to 16 by Re for a laminar flow. Okay. This can be calculated exactly, we will do that later in the course. It turns out that for a turbulent flow, you cannot calculate the friction factor exactly. Okay. Because of the turbulent fluctuations in the flow, which are transporting mass, momentum and energy, we do not yet have a way of calculating exactly what the friction factor is. Okay. However, the friction factor in a turbulent flow depends upon the Reynolds number. It also depends upon what is called the roughness coefficient for the wall, okay, the wall roughness. Okay. The reason is because if I look closely at the region close to the wall, okay, of the pipe, okay, a real pipe wall will have some roughness. Okay. Okay. And this roughness has some length scale, I will call that as epsilon. Okay. And when the flow becomes turbulent, the roughness basically determines the extent of the velocity fluctuations close to the wall of the pipe. Okay. If the wall of the pipe was smooth, then the velocity at the wall of the pipe has to be 0 on a flat surface. Whereas if there are roughness elements, these could redirect the fluid at the wall of the pipe in different directions depending upon the scale of the roughness. Okay. So, therefore, the friction factor for a turbulent flow is a function of both the Reynolds number and the dimensionless coefficient, which is the ratio of the wall roughness and the diameter. Okay. The wall roughness has dimensions of length, and therefore, the ratio of the wall dimension and of the roughness and the diameter is a dimensionless parameter. Okay. And the friction factor plots for a turbulent flow are often shown in what is called a Moody chart. Okay. In a Moody chart, you plot the log of the friction factor versus the log of the Reynolds number. Okay. You plot the log of the friction factor versus the log of the Reynolds number. Okay. I should note that in standard tables, the log of the friction factor usually is the Darcy friction factor. Here we will consider the Fanning friction factor for consistency. Okay. In the Moody plot, usually the Darcy friction factor is what is used and not the Fanning friction factor, but here we will consider the Fanning friction factor. Okay. So, when you plot it on a log-log graph, right, we know that f is equal to 16 by Re, which means that log f is equal to log of 16 minus log of Re. Okay. That means on log f versus log Re graph, you get a straight line with a slope that is equal to minus 1. Okay. On a log f versus log Re graph, you get a straight line with a slope that is equal to minus 1. Okay. As a function of at different Reynolds numbers. And at the transition Reynolds number of about 2100, okay, I said that it is not an exact value, there is a transition that takes place to a turbulent flow. Okay. The friction factor increases discontinuously at that transition. Okay. This is not a continuous change. When there is a sudden transition to turbulence, there is a sudden increase in the pressure drop that is required to drive the flow, and therefore, a discontinuous increase in the friction factor. And the friction factor follows another curve, okay, which decreases slower than the laminar curve. Okay. Therefore, the friction factor in a turbulent flow is much higher than that in the extension or the extrapolation of the laminar flow. Okay. So, this would be, for example, for a smooth pipe. Okay. As the pipe roughness increases, you get different curves, okay, depending upon what the roughness is. Okay. Okay, as the roughness increases, you get different curves, and the friction factor increases as the roughness of the pipe increases. Okay. So, that is the Moody plot for the friction factor versus Reynolds number. So, if you want to know what is the friction factor, what is the pressure difference you require for a pipe for a particular Reynolds number, you would go to the Moody's chart and find out what is the friction factor at that particular Reynolds number. From the friction factor, if you know the average velocity and the diameter, you can find out what is the pressure difference required. Okay. There are also correlations for the friction factor in a turbulent flow. Okay. I will just go through one of these, a classical correlation, okay, which I am going through this only because it is relatively easier to manipulate. There are more exact correlations that are available, okay, which contain more parameters and which do a better job of reproducing what is seen in experiments. I will just discuss one of the classical ones, okay, which is called the Colebrook correlation. Okay, for the friction factor in a pipe flow. This is an implicit relation. Okay. It is written as 1 over square root of f is equal to minus 1.737 ln of plus as expected. This depends upon two things. One is the Reynolds number. One is the Reynolds number and the other is this roughness, okay, the pipe roughness, okay, the scaled pipe roughness and the Reynolds number both enter into this. But you can see that the square root of f is appearing on both sides of the equation. Okay. So, you cannot solve it for a given Reynolds number. You do not get an explicit expression for the friction factor. A couple of points to note here. First thing is that I have expressed it as ln, that is the natural logarithm. Okay. It is usually expressed in log to the base 10, okay. But for consistency throughout this course we will use a natural logarithm, okay, so as not to get confused with the basis of the logarithm. Okay. Similarly, we will use exponentials, we will not use 10 power, okay, exponents. So, because I have defined it in terms of the natural logarithm, this coefficient is different from the coefficient 4 that is usually seen when it is expressed in terms of the log to the base 10. And the other thing is that this coefficient is different, okay, because I have used the fanning friction factor here. In cases where the Darcy friction factor is used, this coefficient will be different. Okay. So, this is an implicit relationship for the friction factor as a function of the Reynolds number. Okay. However, this is actually an explicit relationship if the pressure drop is specified and you want to know what is the velocity. Okay. Recall that the Reynolds number is rho V average, okay, d by mu, and the friction factor, okay, is equal to delta p by L by 2 rho V average square by d. Okay. So, those are the conversions for the friction factor and the Reynolds number. Okay. If I take this factor here, okay, Re times square root of f, if I take this factor Re times square root of f, you will get that Re times square root of f is equal to rho VAV d by mu into delta p by L per half, okay, 1 by, okay, 2 rho per half times VAV. Okay. And you can see that the velocity cancels out on both sides. Okay. The velocity cancels out on both sides. Okay. So, therefore, I will get this as okay. I will have rho, okay, d cubed, okay, by mu square, okay, and I have a 2 here, and I will have delta p by L, okay, per half. Okay. And therefore, this is independent of the flow velocity, it depends only upon the pressure drop. Okay. So, this depends only on the pressure drop, which means that the right side of this Colebrook equation, okay, can be written as minus 1.737 natural logarithm of 1.25, okay, okay, divided by this factor, okay, rho d cubed delta p, okay, by mu square 2 mu square L. whole to the half. Okay. And 1 over root f on the left side can be written as 2 rho VAV square by d into L by delta p, okay, per half. Okay. So, I have the average velocity into 2 rho by d L by delta p whole per half is equal to minus 1.737. Okay. This 2 can be absorbed in the equation. I will get 1.77 mu by root of rho d cubed delta p by L. Okay. So, that is the Colebrook correlation, okay. And you can see that the right side is independent of the velocity. So, if I know what is the pressure drop, if I know what is the applied pressure drop or the pressure gradient across the pipe, I can calculate what is the velocity. Okay. For a given velocity, I cannot explicitly calculate the pressure drop, because the left side does depend upon the pressure drop and the right side also does depend upon the pressure drop. But for a given pressure drop, I can find out what is the velocity. Okay. And on that basis, you can calculate the pressure drop as a function of velocity and then calculate the friction factor, and that friction factor is what is plotted in these kinds of diagrams called the Moody diagram. Okay. And also note that the second term on the right here goes as 1 over the Reynolds number. Okay. So, this term is proportional to 1 over the Reynolds number. Okay. So, as the Reynolds number becomes larger and larger, the roughness of the pipe will become larger and larger, and the friction factor will depend mostly on the roughness of the pipe rather than on the Reynolds number and the friction factor. Okay. So, as I said, this is a simple correlation. I have discussed this in some detail here only to show you how you can do calculations, approximate calculations using this correlation to get a definite result, okay, an estimate. Okay. There are tables available including the Moody chart, which I discussed earlier, and there are more exact formulas that are also available, which can be used to get the Reynolds number as a function of friction factor or vice versa. Most cases those are implicit formulas, and therefore, you cannot explicitly solve to get the pressure drop given a flow rate or the flow rate given the pressure drop. Okay. That is possible only at low Reynolds numbers, where there is a straight inverse relationship. Friction factor is equal to 16 by Re. Okay. Only in that case does a straight can you directly calculate the friction factor and the pressure drop from the flow rate. Turbulent flows are complicated, and therefore, there is no direct relationship. So, this is summary of flow through a pipe for momentum transfer. The important message here is that there are two flow regimes, laminar and turbulent flows. The transition is usually at a Reynolds number of approximately 2100, and the friction factor increases discontinuously at that. The reason is because in a laminar flow, transport across happens due to molecular diffusion, because you have nice smooth streamlines and there is no velocity fluctuations perpendicular to the flow. In a turbulent flow, you have large cross stream velocity fluctuations due to parcels of fluid in correlated motion called eddies, and the efficiency of transport or the transport rates due to these fluid velocity fluctuations are much larger than the transport rates due to the molecular velocity fluctuations, and because of this, the friction factor for a turbulent flow is much larger than that for a laminar flow. These are represented in Moody plots and also in approximate correlations like the Colebrook correlation. Laminar flow, the friction factor is always proportional to 1 over Re. For a cylindrical pipe, the proportionality constant is 16. That is a brief summary of flow in a pipe. Next lecture we will go on to flow past a flat plate and then flow past particles. In this particular case, we will consider in some detail the flow past a spherical particle. I will continue this lecture in the next class. I will see you then.